This work is actually joint work with Professor Omar Kenyu and Professor George Turkiya. And I would also like to thank Wenyu Lee for the help in the finite element code. So what we see here on the left side is a CT scan or MRI picture of a brain. And here in this part is there is an anomaly. And so inspired by this kind of application, we consider the problem of detecting an anomaly within a two-dimensional fractional medium. So on the right-hand side in the picture, the anomaly is being this ellipse, and these dots are actually just some observations. The goal is to develop a computational strategy in a simplified settings. So giving an inclusion or an anomaly of a known shape, for example, a square, a circle, or an ellipse, we want to infer the geometrical features of this anomaly, location, diameters or axes, the rotational angle, and also the physical properties. This includes two things: the diffusivity coefficient inside the anomaly region, and also the fractional order parameter beta, which we assume to be between 0 and 1, as we will see later. So the domain of the problem is like this. So the omega is this big blue thing, and we have an anomaly with a simple E, and it's inside a region called omega internal, and there is an omega external, which is the region between the black dashed line and the blue dashed line. So the methodology is to consider a Bayesian inverse problem with a fractional diffusion PDE that's minus the fractional Laplacian on omega, u equal to a source function f inside omega internal, and u is 0 in the omega external. We will see later why we can such of having these two domains here. So why we consider a fractional diffusion problem, not a classical Laplacian problem? Because anomalies often introduce a heterogeneous diffusion behavior. That means they interact with the outside. And so the classical Laplacian model using only focuses on local interactions. That means the rate of change at a point is determined by only its immediate neighbors. However, the fractional Laplacian operator captures long-range dependencies, non-local interactions, and therefore it's very good for heterogeneous diffusion effects. There are two ways to specify the fractional diffusion problem. So the first way is the fractional Laplacian being a divergence, like the regular divergence of a non-local flux. So the non-local flux is q to the power beta of u, which is defined as minus the diffusivity field times the fractional gradient of u, where beta of x between 0 and 1 and kappa of x is bigger than 0. And the fractional gradient is defined by this operator here. So we have some constant that includes the gamma function, and d here is the dimension of the medium, which in our case would be just 2, times this, and this integral, as we can see here, we have in the denominator y minus x, the absolute value or distance to the power d plus beta x plus 1 times u of y. And this PV means principal value of the integral, which means we are only caring about the finite term of the integral. Then you define the fractional Laplacian to be just the regular divergence of this non-local flux. Now, when kappa and beta are constants, we will get a non-symmetric fractional Laplacian, which is given by this operator. And we can see here now u of y minus u of x appears. And this is actually corresponding to the non-local interactions. So the point x is interacting with the whole domain of Rd through the integral. And one can get rid of this whole constant here, the normalizing constant, by including it in kappa. However, this is the case when kappa and beta are constants, but what we are interested in, kappa and beta are varying in space. And that's why we use the second formulation, which follows a non-local mechanics framework. So the local divergence now, and its adjoint serves as a non-local gradient. This will yield a symmetric fractional Laplacian. So we use a non-local divergence, not a regular divergence. So the non-local divergence operator, denoted by D, is defined as follows. So for a vector field V, define Rd to R, and anti-symmetric vector field alpha of xy from Rd to Rd. The operator is defined as follows. So that the divergence operator on V is the integral over Rd Vxy plus Vyx dot this antisymmetric vector field alpha xy. And antisymmetric property means when you exchange the variables, so xy becomes yx, then you have alpha xy equal minus alpha yx. So that's antisymmetric. And of course, symmetric means alpha xy equal alpha yx. But this is an antisymmetric vector field. The adjoint operator, which served here as a non-local gradient and is denoted by D star, is defined through the following identity. So you have the integral of u times the divergence over Rd minus the integral over Rd times Rd of the adjoint on u times Vyx equals 0. And one can solve for this and get that the divergence is actually, sorry, the non-local gradient or the adjoint operator is minus u of y minus u of x times alpha xy. And now we define the non-local fractional Laplacian operator as the non-local divergence of this kappa, or with the line on the top, times the adjoint of the divergence. And one can easily show that this will be equal to minus 2 the integral over Rd uy minus ux gamma xy dy. And now gamma xy, it's actually a symmetric fraction, a symmetric vector field, is equal to alpha xy transpose times this kappa line xy times alpha xy. So this setting, it actually works for any kappa xy and alpha xy, as long as this gamma here is symmetric and this alpha is anti-symmetric. So one possible choice or possible choices for this diffusivity vector field kappa line is to take it to be the square root of kappa of x, kappa of y times the identity. And in this way, if you change x and y, then you will still have, so you will have a symmetric function. And, or you can take it to be the average kappa x plus kappa y over 2 times identity. If you take it like this, any choice of this, so let's stick with this first one, then gamma x of y becomes, because this is identity, the determinant of kappa xy times the norm of alpha xy squared. Now, since we wanted to mimic the fractional diffusion in the first case, we choose an antisymmetric vector field alpha to be of this shape, and you can see that it's an antisymmetric. So if you exchange x and y, then you will have minus y minus x, which is equal to minus alpha xy. And beta of x here is bounded up below by beta below and beta up, and it's less than 1. So with this choice of alpha and the choice of kappa, we have gamma of xy to be the square root of kappa x, kappa y, divided by the norm of y minus x to the power d plus beta x plus beta y. And finally, our fractional Laplacian, now kappa and beta are varying in space, not like the first case, is given by this operator. Okay. Now, the Will-Boseness of a non-local fractional operator, which is a symmetric one in the second case, generally requires volume constraints to be imposed on an exterior domain. So as we saw here, this difference here, see that the point x, the function at point x is interacting with the function at every point out and outside, so in the whole RD. And in practice, of course, we don't solve the problem on the whole RD, so we cut this domain to some finite subdomain. And therefore, we apply this operator in a bounded domain omega, such that it consists of omega internal union with omega external, and the interaction between them, they are disjoint. But the non-local interactions occurs between points in omega internal and omega external through this difference here. Now, if we set omega external to be actually the empty set, then the problem actually might become elbowed. So we need this omega external. And now our volume constraint Dirichlet problem is given by this 0.4 equation. So minus the fractional Laplacian applied on u equal source function in omega internal, and u equals 0 in omega external. And the fractional Laplacian is as I showed you before. Okay, now we'll focus on elliptical anomaly. So we don't consider a square, or it's been already considered in one-dimensional problem, no, two-dimensional problem before. So we consider ellipse, and our domain is omega is from here to here, which is from minus 0.2 to 1.2, and here also from minus 0.2 to 1.2. And omega internal is the thing in this square, which is between 0 and 1. And our ellipse, which is the unknown, but known shape, so the unknown inclusion is denoted by E, is centered at some location, Cx, Cy, so some point here. And it belongs to 0.3, 0.7, each of the Cx or cy. We have the major axis A of the ellipse, the minor axis B, and the rotational angle theta. So actually, all of these will be unknown, and we would like to infer them. We also consider the case where the diffusivity inside the ellipse is a constant but unknown, so called kappa n. Outside the ellipse is known, and it's kappa out. And the fractional parameter inside is beta n. It's unknown as well. And beta out outside is known. So we have actually 1, 2, 3, 4, 5, 6, 7 unknown parameters that we would like to infer using our Bayesian inverse problem. We also assume that the right-hand side f of x is like this. So inside the anomaly is a constant, and outside the anomaly is another constant. Okay, so in order to use this fractional Laplacian, we have to deal with some challenges. First of all, this is actually a singular integral operator, and when you discretize it, you will end up with dense discrete matrices. On the other hand, if you use the regular Laplacian, when you solve the Poisson problem, you will get a very nice mass matrix, like sparse. It's a sparse, and you have, dense blocks on the diagonal. But this is not the case here, and this will, of course, create issues with the memory and also the computing requirements. We also have lack of smoothness at the boundary of the anomaly. So generally, only low-order spatial convergence can be achieved, and the steep variation of solution with uncertain inputs as well. And this, of course, will be an issue when you in the inversion, so in the Bayesian inverse problem.
Hamza, I'm sorry. Alexander here. Can you please go one slide back? I just have some questions.
Yep, here?
Yes, exactly. So we are trying to identify maybe 7 unknown parameters, yes?
Yes.
I just was thinking maybe to put this anomaly in a bounding box and just then you reduce dimensionality, so you identify only center of this box. And why do we need such detailed identification of this anomaly? Is it some just small box not enough?
Uh, uh, that's actually a good idea. But generally, what you are giving this whole image. So you are giving this whole image, and there is an anomaly somewhere, but you don't know exactly, because in this picture it looks nice. You can see the anomaly, but in other pictures, as I will show later, you barely can see the anomaly by your own eyes, and you would like to provide a solution, like how to determine the location of the anomaly, exactly the orientation of it, and what about the axes. In this case, okay, so if you want to put a box around it, you of course you need to use, of course, image processing tools to determine the boundary of the anomaly first. But then, okay, you'll determine the axis, the major axis. What about the minor axis? It will be difficult if you put a box, and therefore it will be hard to find the center maybe of the anomaly.
And then just another, maybe to use here k-means, so we give us an input set of pixels, blue pixels and red pixels, and then you run k-means algorithm which try to find clusters, and it will identify this red spot as a cluster. So you do
So this is we use something like that. I will talk about it later on. So I will split the problem into two cases. I will call it fully Bayesian, where I infer the 7 parameters, and semi-Bayesian, where actually I use some image techniques to determine the anomaly and therefore find these geometrical parameters, but then use the fractional Laplacian to only find the kappa n and beta n. So we're going to use something like that.
I'm asking because we do fraction detection. So is it fraction has also thickness and angle and 3 angles in space.
Yeah.
Do you see some similarities between your problem and this fraction detection?
Yeah, this is actually considered a fractional detection, anomaly detection problem.
Okay, thank you very much.
Now we move to the weak formulation because we're going to use finite element technique to solve this. So we define the energy space, which is V belongs to L2 of omega. The V norm, which is going to be defined below here, is the L2 norm of V plus the semi-norm right here, less than infinity, and V equals 0 in omega external. So multiply by a test function V and integrate. Then we note the following. So this on the left-hand side integral is this guy here. Now switch the variables and note that gamma xy is symmetric. Then, so I'm gonna just do change of variables. Instead of x, I have y. Instead of y, I have x. Then also this guy here is equal to now -2 of this double integral ux minus uy gamma xy v of y dy dx. And sum the two equations and divide by 2. Now you have the left-hand side here is equal to this bilinear form. And this bilinear form actually satisfies the Cauchy-Schwarz inequality and a Poincare type inequality, and therefore it guarantees the Will-Boseness of the weak problem. The finite element. So consider a triangulation of omega, which is the union of interior triangulation and exterior triangulation. And we'll consider a finite element space, V of t, which is a subset of V. And this is actually a finite element space of continuous piecewise linear functions. And we define the nodal basis functions to be psi, not going into details. And you write u of x and v of x to be in terms of these finite element basis functions. Then the discrete bilinear form is the sum of this small double integrals a t t prime, where t prime are triangles in the triangulation capital T. That's on the left-hand side equal to the sum of bt, the right-hand side, where for each t belongs to t internal here. And that's because the f, the source is 0 on t external. And this AT prime is the double integral of u of x minus uy, vx minus vy times gamma xy over small triangles t prime. And BTV is the integral of the source function times the test function v of x over a triangle T belongs to T internal. We split this bilinear form into three components. The first component is when T belongs to T internal and T prime belongs to the whole triangulation T, which is T internal union T external. But T and T prime, they intersect by an edge or by a vertex, or they could be the same. And that's actually gonna result in kind of blocks on the diagonal. The second is when T and T prime in T internal, triangulation internal, but these triangles, they don't intersect. And this actually shows the effect of tau, the triangle tau, on all non-neighboring elements of the mesh inside T internal. And in fact, this part is constructed using the so-called hierarchical H2 matrix, which is a way to write matrices in low-rank representation. And this will result in linear complexity and storage and operations. So you have O of n, where n is the number of nodes. The final part is T belongs to T internal and T prime belongs to T. And now T and T prime also do not intersect. And this is actually the effect from all non-neighboring elements of the mesh, including elements in T external on T. However, this is written as a weighted mass matrix with a mass density representing the effect of the global mesh at every integration point. And to compute this density, we use a fast multiple type method. And also this will result in a linear complexity in storage and operation. Okay, now we move to the Bayesian inverse problem. So we consider two approaches. And this is to answer Alexander's question. So the first approach is to generate a 7-dimensional surrogate in order to call the solver inside the MCMC routine. And in this we will infer both the geometrical and physical properties. So all 7 parameters. Sorry. However, in the second approach, we take advantage of the singularity of the solution across the anomaly's boundary. In fact, the gradient, actually the second derivative is not continuous, and we consider this in order to determine an optimal fit of the anomaly using image processing. And as a result, you already determined the geometrical parameters. So as a result, you only need to use MCMC and this surrogate building in 2 dimensions. And in that case, we only need to infer kappa n and beta n. So a framework for the Bayesian inverse problem. So let lambda, capital lambda, which is a vector lambda 1 up to lambda n, and n could be 2 or 7, either 2 parameters or 7 parameters. Now, we represent each lambda I as a random variable by this transformation. So each lambda I belongs to an interval AI BI. For example, Cx and Cy, the centers, belong to 0.3 up to 0.7 interval. But we consider them as uniform random variables. So using this transformation, where psi or xi belongs to is a random variable in -1, 1, we have now this transformation that takes lambda I to be in AI BI. And we define our inverse problem as follows. So consider X with some norm and Y, some norm to be Banach spaces, and assume that U is from X to X. Then the inverse problem is to determine these parameters lambda in X given noisy data Y, which is some operator of the random variable U of lambda plus some noise, Gaussian noise. This Gaussian noise belongs to the Gaussian with mean 0, or sampled from the Gaussian with mean 0 and positive trace class self-adjoint operator gamma on gamma, or gamma on Y. That's what. And we define the posterior of the problem then to be the likelihood of these, the prior of these parameters was just a multiplication of uniform priors densities times the exponential of -1/2 minus square root of gamma Y minus the observational operator applied on U in the Y norm squared. And then the maximum a posterior estimator or map estimator is to maximize this probability, which means to minimize this, this thing here. And so you look for a lambda map that augment of this term. Now, of course, inside MCMC, usually in Bayesian inverse problems, you have to run MCMC or whatever method you use hundreds of thousands of times. And you cannot call the solver each time. It's not practical at all. It's especially when you do this kind of fractional diffusion operator. Although we do some cost reduction in the memory and operations, still when we, for example, use a mesh of size 0.02 and consider like 3 refinements of the mesh, which will end up with 131,000 of nodes, still the solver will take several minutes to finish. And you can imagine if you want to run MCMC 100,000 times, then this will take months to run. And therefore, we consider a different approach where we estimate the solution of the fractional diffusion at a given random input to be given by this summation is called the polynomial KAUST expansion. So here, recall that xi is just a random vector, uniform random vector on -1, 1 to the power n. These CKs here are called the polynomial KAUST expansion coefficients. And these psi k c are orthogonal, n-dimensional, multivariate Legendre polynomial of order R. And the number of terms, capital P here, is +1 because we have 0 here, is R plus n, where the n is the number of parameters, factorial over R factorial, n factorial. So for example, if you want to consider multivariate Legendre polynomial with order 5, and in the case of inferring 7 parameters, then we will have 792 terms in this expansion. And if you consider the order 6 of these polynomials, then the number of terms will be 1,716. And this psi k xc is actually defined as the product of the univariate Legendre polynomial of order alpha I k and evaluated at xi, where alpha I k is a member of a multi-index set alpha k. So in fact, computing these orders is not easy, and there have been studies on how to do that. We consider an algorithm from a certain book, where for each k, we compute these alpha k's, the orders of these univariate polynomials, in a kind of a tensorized way. Okay, so if you consider the probability space omega, this is different from the omega, the region I was considered before. So this is just a probability space on which this random variables u of lambda of xi are defined. Then the Legendre polynomials, the multivariate Legendre polynomials, are actually orthogonal on this probability space with respect to density q of xi. And it's just here 1/2n, because xi is uniform random variables. So they are orthogonal. That means when you take the product of psi q with psi k prime, they will be 0 unless k equal k prime. And therefore, you can evaluate ck by multiplying by ck prime here and take the integral of both sides. And ck will be equal to the right-hand side here. Now, when n is small, for example, it's 2 or 3, one can use a Gauss-Legendre quadrature rule to approximate this integral here. So you choose some Gauss points in the interval -1 to 1 to the power n, and you can get this coefficient ck quad by this formula. However, when n is larger, one should use a different approach, and we use a regression-based approach. That is, we minimize the distance between a set of solutions. You have m solutions at known x's, and this is in a vector u in Rm. You want to minimize the distance between these solutions and the surrogate model. So now the choice of m is important. When m is like greater than or equal 3 times the p, which is the number of terms in the expansion, one can use the least square approach. So you minimize the L2 distance between the solution and the surrogate, and it's given by this, where z here has the entries ik, which is equal to the multivariate Legendre polynomial k evaluated at xi of I. However, when p is large, solving the model for m equal 3p takes several days. And so we might actually have like m around p or smaller than p, and then solve a regularized L2 minimization problem. So in this case, you you minimize the L2 distance, but also you add a penalty term where this regularization parameter gamma is optimized using a cross-validation. This is called the lasso model. And adding this term will make the matrix, the problem more sparse. And so solving it will be much easier. So I denote this by C reg regularized, and this is C SQ least square, and C quad when n is 2, C quad for using the quadrature rule. Okay, now we come back to the semi-Bayesian inference. So as I mentioned, actually, if you look at the solution on the major and minor axes, here is the solution, and the blue is on the major axis and the red in the minor axes. You will see that at the boundary of the anomaly, the solution is sharp, which means if you take the gradient there, it's going to be discontinuous on the boundary of the anomaly. So we take advantage of this, and in order to determine the regions of high and low gradients, and therefore determine the pixels with the gradient jumps surrounding the boundary. And these will be labeled as V, X, I, Y, I from I equal 1 to T, the number of pixels where you have a jump in the gradient. We use two ways to determine the ellipse boundary. For example, using the so-called Char filter. So the idea is to apply the Char filter twice. So here's the given image. You apply Char filter and then take the norm of that, and you apply the Char again on the norm. Then you raise it element-wise to the power 4. And then you look at where are the high values. So you take this image prime, this is image prime. Where is it bigger than 0.1 times maximum of image prime? And this will result in this red region. And then you solve a minimization problem in order to find a fit for the ellipse. And so this is the minimization problem. So you want to minimize this function G, where G is given by this. So because there's no time, I will skip this. But this is the idea to take advantage of the singularity around the boundary of the anomaly to find a fit for the anomaly using just image processing. And of course, this way, you know the geometrical features of the anomaly. It remains to find the physical features, kappa n and kappa and beta n. Okay, I move now to the numerical results. So I'm going to show two cases here. The first case, we set the source function to be 20 inside the anomaly and 0 outside. And also we set beta out to be 0.5. Actually, I forgot to mention also kappa out is 1.5. For the second case, the right-hand side, we set Fn to be 20 and F out to be 20. And that's why you can barely see the ellipse. And also beta out to be 0.5. And we consider that we have 100 observations in the image. So in fact, the pixels that we have is 10,000 pixels, but you are only observing 100 of them. So, and this is of course a very challenging problem. Number of observations very low. So how reliable are the surrogates? In the 7-dimensional scenario, case 1, here I have the case where the order, so P here is actually R, in my case, the order of the multivariate Legendre polynomial. So when it's 5, I have 792 terms. And I'm taking M, the number of solutions or realizations of the model, to be 4,000, which took about 5 days to compute. So I have 4,000 of solutions at random variables in the 7-dimensional cube. And then I consider the least square model because 4,000 is much greater than P. So when you use the least square, here's the original image, and this is the solution, the exact solution, and this is the one you get from the surrogate model using this 4,000. And this is absolute difference. And if you take the relative error, you measure relative error, it's of order 10 to minus 2. Now, what if we just consider 1,000 solutions? So this is very close to P. In this case, you use the lasso model, and that's down here. And you get also very similar relative error. But of course, 1,000 is much cheaper than using 4,000. This will take 1 day to run to find these 1,000 solutions, random solutions. And so now in the case where P equals 6 or R equals 6, the order of the multivariate Legendre polynomial, you have more terms, 1,700 terms. So with 4,000, you use least squares and also the relative error 10 to minus 2. And when you use now lasso, look, now M is less than 1. It's about half of the number of terms, but still you get a very good relative error. It's actually better than the least square error. Okay. So I'm just showing 2 different ellipses. So this one here, and this is another one. And in second case, the same thing, 2 different random images, and we look at the errors. But now in this case, it's actually on the order of 10 to minus 3 in both lasso and least squares for both different realizations. So they are okay. The surrogate model is okay. As for the semi-Bayesian problem, so looking at case 1 and case 2, using this star filter in the first one, and actually I use a different method called gradient filter in the second one, we were able to find a very good fit for the ellipses. So as you can see here, the true ellipse is the top, so in the center 0.6, 0.45. Here you get 0.59, 0.44. The major axis is perfect. The minor axis perfect. Theta is also good. In the second one, it's a bit harder, and that's why I couldn't use this star filter and use a different way called the gradient filter. And it's harder because Fn and Fout are the same, and so determining the boundary of the anomaly was kind of hard. But Now in two-dimensional case, just we have kappa and beta n. So how reliable are the surrogates? They are very, very good. So we use, remember, when n is 2 or 3, one can use the Gauss-Legendre quadrature rule to approximate the integral. And so here we use only 25 Gauss quadrature points. And we can see for two different problems in case 1 and case 2 that the error, for example, here is epsilon on the order of 10 to minus 4. Here it's on the order of 10 to minus 3. And here it's on the order of 10 to minus 2. Okay, now we move to Markov chain Monte Carlo. Of course, we use a Markov chain Monte Carlo. In fact, we use a Metropolis Hastings MCMC algorithm to sample from the posterior. However, because the problem is large, seven-dimensional, we get a lot of, and and each parameter is in bounded interval, we get a lot of rejections, which is okay. But one can avoid that by transforming the parameters to minus infinity to infinity through this transformation, and then you multiply by the determinant of the Jacobian, and you get the new posterior. And here's the results of case 1 in the fully Bayesian, so 7 parameters. So here's the given image, the true solution, and this is the learned one. We can see that if you look actually at the values, that they are okay, except the theta. So learning theta was difficult, and that's why you can see the shape is going to the left. It's not oriented as in the true image. But the relative error is very small, 10 to minus 2, which is okay. And this is the case in semi-Bayesian. So you determine the geometrical features using image processing, and you see that they look exactly almost the same position, same orientation, axes, and then you use MCMC to learn kappa n and beta n, and it was also pretty good. In the second case, also we have this. So, for example, theta for the map estimator was 1.2, while the true is 1.14, and when you use the mean estimator, it's 1.4. Yeah, you're taking the difference is absolute difference, and this is the relative error, 10 to minus 2 as well. And this is the case and when you use image processing, and also you get very good results. And that's it. I'll stop here. Thanks for listening.
Thank you very much, Hamza.